Hello and welcome back. We are continuing our adventures into parametric equations. Today we're going to talk about speed and arc length. We know that parametric equations can be used to describe the path of an object moving in a plane. This leads to ask the question, how fast is the object moving at any given point and how far has the object gone? A particle moving along a curve in the plane with parametric equations, x equals f of t and y equals g of t, where t is time, has a speed given by this guy or this guy. Same thing, but what are we looking at? We have the derivative of the x component squared plus the derivative of the y component squared, and then add those together and take the square root. Should look maybe a little bit like the distance formula. And on the right, we actually have the same thing. Derivative of the x component squared, derivative of the y component squared, add those together and take the square root. So let's practice this. The position of an object moving along a path in the xy plane is given by these parametric equations. X of t equals 5 sine pi t, and y of t equals 2t minus 1 squared. So let's find the speed of the particle at time t equals 0. So for the speed, we need the derivative of the x component and the derivative of the y component. So the derivative of the x component using the chain rule is 5 pi cosine of pi t. And at 1, we get 5 pi times cosine pi, so we end up with negative 5 pi. For the y component, we have a derivative of 2 times 2t minus 1 times 2. That's the chain rule again. And if we plug in 1 to that, we have 4. So we have the derivative of the x component, the derivative of the y component. So under a square root sign, we can square the derivative of x, square the derivative of y, and add them together. Now we're going to move into arc length in parametric form. If a smooth curve C is given parametrically by these equations, x equals x of t and y equals y of t, then the arc length L of C over the interval from A to B is, oh, look at this. Here's the speed, and we're just integrating it from A to B. Sound familiar? Very similar to just our regular particle motion, we've just got two components going on here. So we can also refer to this as distance traveled. Example 2, what is the length of the curve defined by the following parametric equations? We've got x of t equals t squared minus 2t, and y of t equals t cubed minus 4t. And we want the length of the curve from 0 to 2. So we'll take the derivative of the x component and get 2t minus 2. We'll take the derivative of the y component. We'll get 3t squared minus 4. All right, so here we go. We are integrating from 0 to 2. We'll take the derivative of our x component and square it. We'll take the derivative of our y component and square it. Add them together, take the square root, and there we go. We have an arc length of 6.511. Now we have an ellipse defined parametrically by x of t equals 1 plus 2 cosine t, and y of t equals 3 sine t. What is the perimeter of the ellipse? All right, well, it's going to take us 0 to 2 pi to draw it. And the perimeter of the ellipse, guess what? It's just the arc length. So we'll find the derivative of our x component and the derivative of our y component. And same thing. We're going to integrate from 0 to 2 pi. derivative of our x component squared, the derivative of our y component squared, add them together, take the square root, and the perimeter of our ellipse is 15.865. All right, there's a lot going on in this one, but I like it because so much of calculus comes together. At time t, the position of a particle is moving in the xy plane and is given by our parametric functions x of t and y of t. Now, the information we're given is the derivative of the x component and the graph of y. We also know that at t equals 0, the particle is at the point 4, 0. So 4 is an x position and 0 is a y position. Part A says, find the slope of the tangent line to the path of the particle at t equals 3. All right, so we're looking for dy dx. Well, at time t equals 3, the slope of my y function is -2. So there's my dy. And then my dx, since they've already given us the derivative, we just have to plug in 3 to that. So my dy dx is -2 over 9 plus sine 9. Now, if you want to pop that into your calculator, you get -0.21249. Find the speed of the particle at t equals 3. Well, this is great. We already have the derivative of the x component and the derivative of the y component. So we'll just square each of those, add them together, take the square root, and there we have our speed of about 9.6222. Part C, find the position of the particle at t equals 3. All right, so we've got two problems we got to work on. We need the x position and the y position at t equals 3. So to find the x position, we're going to do the starting point of 4, and then we'll integrate the derivative from 0 to 3. So our x position is at 13.7735. Now the y position, remember this is the graph of y. So at 3, the y position is 4. So here we go. At time t equals 3, we have a position of 13.7735 and 4. And of course, all this is leading us to, you guessed it, the equation of the tangent line. And we have a slope, and we have a point, so we have a tangent line. Speed and arc length of parametric functions. Not a whole lot of new stuff, just looking at it from a different perspective. Thanks so much for being here. See you next time.